Welcome to this new episode of Neural Muse, the podcast about technology and artificial intelligence. Imagine wanting to create a realistic image of a virtual scene, with lights, shadows, and reflections that behave just like in the real world. Traditionally, this process, rendering, relies on simulating how light moves through the scene using methods like Monte Carlo path tracing. These methods are accurate, but computationally intensive, requiring complex recursive algorithms and suffering from noise. Recently, neural rendering has emerged as an alternative, learning to predict how light behaves without explicitly simulating it. However, approaches like neural radiance fields, NERFs, tend to overfit a single scene, needing dedicated training for each new one. They also use scene representations incompatible with standard 3D modeling tools. RenderFormer changes the game. Instead of treating rendering as a physical simulation, it views it as a sequence-to-sequence transformation. It takes a sequence of tokens representing triangles, with reflectance and emission properties, and transforms them into tokens representing small pixel regions. Unlike traditional methods, RenderFormer doesn't explicitly solve the rendering equation, or use recursion. It learns to approximate light transport directly, without Monte Carlo noise or custom rendering algorithms. Being fully neural and differentiable, it requires a one-time, expensive training process, but can render new scenes without retraining or per scene adjustments. Its biggest advantage is generalization. RenderFormer can render scenes and objects it never saw during training. And since it uses triangle mesh inputs, standard in 3D design, it integrates seamlessly with existing modeling tools. RenderFormer's architecture consists of two transformer-based stages. The first stage is view-independent and models light transport between triangles. Instead of typical 1D positional encodings, it uses relative 3D spatial encodings, essential for accurate light modeling. The second stage is view-dependent. It processes tokens representing ray bundles, e.g., 8 by 8 pixel patches, using cross-attention to match them with relevant triangles and output the final pixel values. RenderFormer supports full global illumination, multiple reflections, fine shadows, soft and hard lighting, indirect diffuse light, glossy surfaces, and multiple light sources. Unlike many neural methods limited to local shading or point lights, it handles far more complex lighting scenarios. That said, it has limitations. Currently, it supports scenes with up to 4096 triangles due to the quadratic scaling of transformer models. It was trained with a single reflectance model, up to 8 light sources, and with the camera positioned outside the scene bounds. Going beyond these conditions may reduce detail, but generally degrades gracefully. For instance, it can handle more lights by rendering each one separately and compositing the results, or handle more triangles with some loss in fidelity. The future potential is significant. With broader training data, RenderFormer could support complex materials, e.g., transparency, subsurface scattering, varied light types, and dynamic camera setups. Its differentiability makes it ideal for inverse rendering, inferring scene properties from images. And with architectural improvements like hierarchical attention, it could scale to much more complex scenes. In short, RenderFormer represents a major step toward fully neural rendering, offering a flexible, efficient way to model light transport without traditional simulation, and moving us closer to real-time photorealistic image generation. Thanks for listening to this episode of Neural Muse podcast.